Moving on from horizontal friction, we're going to look at friction on a slope. That's meant to be a slope. This follows exactly the same pattern. It draws in what we've done in the last two sections. So we're looking at friction. We're still dealing with motion, so we're going to be looking at F max and mu r. But because we're dealing on a slope, our resolving directions are going to be perpendicular and parallel to the slope rather than horizontal and vertical. One of the things that you've got to remember in all of this is R, the reaction force. It's called the normal reaction force because it always acts normal to the surface. On these questions we're going to have a slope with our particle on. So your weight acts straight down, but your reaction goes at an angle. That's just something you've always got to bear in mind. Weight straight down, reaction perpendicular to the surface. So let's jump straight in with an example. Now this one, just to keep you on your toes, they've given you this tan theta equals 12 over 5 again. So hopefully you can remember the first thing we said to do was draw a quick right angle triangle out. Tan theta equals tons of acorns, opposite over adjacent. So this must be, if you know your triangles, it's a 5, 12, 13 triangle. It's a really good idea to learn those Pythagorean triples because they do come up quite often. So off the back of that, I'm just going to write down that cos theta equals, can't always have adjacent over hypotenuse, and sine, silly old hens, 12 over 13 opposite over hypotenuse. So we've got those values for whenever we need to use them. So let's get on with the rest of the question. We're dealing with a slope, so let's first make it a proper force diagram. I've got mg there. Now because I'm on a slope, I'm immediately going to put in that this is angle theta. I'm going to have r. Now looking at this, the only other force I can have, something on a slope will want to slide down the slope, which means I'm going to have a friction pulling me up. So that was a diagram with no forces, and we've been able to create a complete force diagram from that. So now just starting our resolving. So we're going to resolve perpendicular to the surface to try and find r. So that gives us r is positive. Friction doesn't come into it because that's at 90 degrees to where we're operating. So we then get minus mg cos theta. We're in equilibrium in this direction because we're not lifting off the surface. Sticking all the values in, we know we get r is equal to 30g times cos theta is 5 over 13. So r equals, quick bit of working out there, 30 times 9.8 times 5 divided by 13 gives us 113.1. Let's just check our F max. F max equals mu r. So we've got our mu is 0.45 times our r, which is 113.1. Again, on your calculator, use that previous answer. Don't ever use a rounded value. We get F max equals 50.88. So we could well be accelerating here. I think we are. So let's check. Let's resolve. Now I think I'm going to be accelerating that way, so I want to resolve down the slope. It's always better to resolve in the direction of the acceleration. Makes life easier. So resolving down the slope gives me, r's not involved, I get mg sine theta, take away fr equals ma. Newton's second law, that's why we've got the ma. Now work that through with our values. Mg is 30 g times sine theta is 12 over 13 minus 50.88 equals 30a. So 30a equals So 30a equals 220.5. So a equals 7.35. Job done. Have a go at the questions highlighted on that page. So the selection of questions from page 55, exercise 3C.